Okay, so here's where we were talking about last time. We were talking about the Gramschmidt process. Keep in mind what the Gramschmidt process is. And let me just go back a couple pages here. The idea is if you have a basis, maybe you come up with a basis by some method, who knows what, you get some sort of a random sort of basis. And if you think to yourself, well, look, I sure wish I had an orthonormal basis and I would like to convert my random non-orthonormal basis into a basis that is in fact orthonormal, so I can take advantage of all these wonderful features of orthonormal bases. Then the process is the Gramschmidt process. Again, don't be impressed. The idea is, for example, when you realize that one of the vectors that you have is not pointing in the direction that it should be, well, shove it over. Right? Push it until it's pointing in the direction that it should be. All right, and we derived formulas. Here's our sort of, here's the n equals 3 case, the way you get something pointing in the correct direction. The big idea, of course, is that which you subtract is just the part of the vector that you're trying to fix that points in the direction that it shouldn't be pointing, right? It's a real simple breakdown. Anyway, make sure to understand the reasoning, make sure to remember the formula for how to subtract off those appropriate bits. And so let's get our hands dirty here. I'm going to mostly skip the arithmetic. It's just arithmetic. I just want to kind of highlight some aspects of the process, so you see it going. So we start off with a basis, and you notice here that this basis is not particularly nice. It's not orthogonal. None of the vectors are unit vectors. It's just nothing particularly great about this basis. So let's fix them. This vector, what's wrong with that vector? Well, it's not a unit vector. Okay, well, we will turn it into a unit vector by dividing it by its own magnitude. Again, the first vector is always easy to fix, right? But now, with that first vector fixed, I have a V1 now. So I've got myself a good V1 vector. How do I fix the second vector? W2. W2 has a couple of problems. It's not a unit vector, but it also is pointing in a problematic direction. To some extent, W2 is pointing in the V1 direction. It's not supposed to point at all in the V1 direction. It's supposed to be orthogonal to V1. So we're going to fix that direction problem by subtracting, whatever extent to which it's pointing in the V1 direction. So taking the vector we're trying to fix, looking at its component in the V1 direction, that much of V1, that's how much it's pointing in the wrong direction. This is the part of W2 that's a problem. So let's subtract from W2 the part of W2 that is a problem. And the result is a vector here. And now you got to do some arithmetic. Right? You got to go through and do all that arithmetic. But the result is a vector that is not in any extent pointing in the direction of V1. So this is a vector that has no problem with the direction. And of course, now annoyingly, we do then have to fix the magnitude before we can declare victory. Right, so I've got to take that vector, divide it by its own magnitude, and there's our second fixed vector. Okay, arithmetic. Right, make sure you can do the arithmetic. By the way, also, another thing to keep in mind as we go through this process, notice this process is happening in R3. We're looking at a basis for R3, using the regular dot product to turn R3 into an inner product space, right? But all of the same ideas apply if you are in a different inner product space. It might be R3 using a different inner product. Possible, right? But it also might be a completely different inner product space, completely different underlying vector space, and then of course a different inner product. So there's a bunch of old exam questions that I encourage y'all to go take a look at where same process, same formulas, it's just that the inner product here, as written in this formula, actually is a non-dot product inner product, right? So this might be the L2 inner product. on some vector space of functions, inner product space of functions. Right? In which case, instead of computing a dot product in the Math 212 sense, well, you're going to have to compute whatever inner product that is. And so it's a super annoying, but you might have to compute an integral, for example, just to evaluate that inner product. Anyway, structurally, everything's the same. It's still all the same formulas. You just have to adapt the inner product to your context. Okay. Likewise, for the last vector, we have a third vector there. What's wrong with that third vector? Well, it has a problem. Let's see, color choice. It has a problem in the V1 direction, and it has a problem in the V2 direction. Now I'm going to have to identify both of those and get rid of both of those. Now it's, again, it's a matter of sort of recopying and doing it. But here are those components. Notice that the inner products, in this case, we're in R3. Those inner products are dot products. So you got to punch it up and subtract those things off, and the result is a vector. Oh, and let's see, there's more arithmetic down here. The result, oh man, this arithmetic's brutal. The result is a vector that at least is pointing in the correct direction. Now again, this is not a unit vector, but again, you can divide it by its own magnitude and you get a unit vector. Okay. All right. So one last thing I want to show you is a trick for this last little bit. An easy way to take this vector and divide it by its own magnitude to get a unit vector. There it is, by the way. There's let's say our blue vector that we need to find the unit vector pointing in that direction. I guess I could divide by its magnitude, but yikes, the arithmetic, right? Brutal. Here's the neat observation I'd like to point out. If I were to take that blue vector, let me do this. If I were to take that blue vector and look at any other multiple of it, any positive scalar multiple of it, like that purple vector. If I were to take this purple vector and divide it by its own magnitude, notice I'd get the same unit vector as a result. Right? So, nice upshot. You can take this blue vector here, you can multiply or divide by any positive scalar at your heart's content before you normalize, and it won't affect your answer. Right? So here's my thinking on that. How about first thing? I'm going to multiply by 245 because I don't like fractions. Right? Perfectly fine, no problem. If I were to unitize that vector, I'd still get the correct unit vector. And then I look at that and think, let's see, 392, 196. Oh my gosh. One's a multiple of the other. Right? 392 is exactly 2 times 196. I got an idea. How about I take this whole vector and divide it by 196? And that leaves me with 0, -2, 1. So instead of taking this monster of big numbers and fractions and computing its magnitude, nightmare, etc., how about fooey on that? I'll just divide this vector by its own magnitude. It's much easier. So that's a nice little trick. It'll save you some pain. Notice that it totally works, right? And some of that development is there, but notice here is the final answer, and it's the right final answer. Okay. Yep.
Wait, so where did if you took away the denominator, how did you get the over root 5 there?
Oh, yeah, so the point is you do still have to, you can multiply and divide by whatever fraction by whatever real numbers you want, but once you end up with some vector that's pointing still in the same direction, you do still have to turn it into a unit vector, right? I'm not saying that this is a unit vector, clearly not, right? But this is, despite not having really done any real work on this is a vector that at least is pointing in the correct direction. And then, so this here is normalized. Yeah. Yep. How did I get it to what now?
Divided by 245 because we originally had that.
Oh, let's see here. What did I do? It looks like I probably noticed, instead of the way I went through it here a second ago, it looks like I may have noticed a common factor of 49. It doesn't matter, right? I mean, it gets us to the same answer, but a common factor of 49. And so, yeah, so you can take this vector and divide it by its own magnitude, but again, with the fractions. Why? How about, notice, get rid of the denominator of 5. Then notice there's a common factor of 4, and again, it's just, makes your life simple. Okay. Right. So, moving along. I do encourage y'all, by the way, to go through my old exams and look for Gramschmidt problems and see how the algebra looks a little bit different. It's less chock full of arithmetic and more chock full of integrals in cases where you have L2 inner products. Okay. All right. Okay, so on to section 9.3. Here's where I have to make a confession. I have been deliberately sweeping under the rug a subtle point, and very few students ever catch this little sloppiness that I'm guilty of. Again, I did it on purpose. I do it every semester. Right? So one student did notice this, and so very happy about that. But anyway, here's what I did wrong. On several occasions in the past, having defined vector spaces, notice that if you look back at chapter 2, I defined vector spaces over the real numbers. Right? And let me remind you what that definition is. I've got it punched up right here. Here it is. This is from chapter 2 notes. A vector space over the reals. It's a set with an addition and a scalar multiplication, and notice that scalar multiplication has to be by real scalars. The scalars have to be real. And then further, notice down here in several places, these scalars have to be real. Having made that definition, in several places, I have totally violated that rule. Totally. Here's a couple of examples of it. Now here we jump up to chapter 4. You may recall we were looking at complex valued solutions to constant coefficient linear differential equations, right? And we multiplied it out and found that, I can view those as linear combinations of real valued solutions. But wait a minute, these are linear combinations of functions. Yeah, sure they are, but check out the scalars. That scalar there is not real. I'm not allowed to do that. So that's technically a problem. Now, good news, and I hope this isn't a surprise, but I did this, I committed this little micro crime knowing full well that this is actually not going to be a problem. So there is a way to fix the little law that I broke here. It's fine. All the results that we did in chapter 4 are fine. It's just that in order to do it really correctly, I would have had to have a conversation that I didn't really want to have at that time. We had enough going on as it was, right? Plenty to keep track of, and so I deliberately swept this under the rug, knowing that I'd have to come clean it up later, and here we are. Okay, so that was one of them. And then here's another one. We were talking about eigenvectors and eigenvalues, and I made this observation that, even though you have a real matrix, if you play the game and go through and find the eigenvalues, those eigenvalues might be complex, and you can correspondingly find the eigenvectors, and those might be complex as well. And so what's the problem with this? Well, the problem is that we were talking about, AV equals lambda V. These vectors, V, are vectors in, they were supposed to be vectors in Rn, right? And now they're not, and furthermore, You can see here as well, I'm multiplying them by complex scalars, violating the rule again that we set here that the scalars are supposed to be real. Okay, so again, though, this is a victimless crime. This can all be fixed. There is a perfectly reasonable way to address this. It's just I'd have to put some machinery around it that, again, would be a distraction from what the point was that we were dealing with. And so, again, I swept it under the rug, knowing that we could deal with it later. So, anyway, here we are. And the simple fix for both of these is I just have to define a different thing. I have to define something called a vector space over the complex scalars instead of a vector space over real scalars. And it's no problem to write it down. You could write down that definition yourselves already. It's pretty much the same definition as for a vector space over the reals. Just allow your scalars to be complex, right? No problem. Okay. Why didn't I do that before? Well, because I wanted to be able to talk about stuff in RN. Right? RN is relatable. We can draw pictures of it. Once you have complex scalars, well, now you have complex vectors, and that's not in RN, and it's hard to draw a picture of. Okay, so the next question I want to address is, now we have vector space over complex scalars. Previously, we've been talking about vector spaces over real scalars. If it didn't matter back in Chapter 4, and if it didn't matter previously in Chapter 5, why does it matter now? Can't I just say, okay, yeah, sure, allow scalars to be complex? What's the big deal? And the thing is, it does change some things. So there are certain situations where having complex scalars really does change things. And it is a problem. And we can't just sweep it under the rug. We will get dramatically wrong answers if we sweep it under the rug. And I want to show you a couple instances of that being the case. So let's think about dimension. This little subtlety, allowing complex scalars, fundamentally changes the notion of dimension, which is a creepy thought. Okay, so quick example. Let's think about the complex plane itself as a vector space with complex scalars. Now, keep in mind, what does it mean to be a vector space? Well, you've got to be able to add things. No problem. You've got to be able to multiply by scalars. Cool. The vectors are complex numbers, elements of the complex plane. My scalars, also complex numbers. Right? And with this in mind, what's the dimension of the complex plane? And I claim that the dimension is 1. The complex plane is 1 complex dimension. Now, how could that possibly be? It's, for crying out loud, it's a plane. It's right there in the name. Complex plane. Planes are 2-dimensional. How could it be 1-dimensional? Well, I point out this is a basis. The number 1 by itself is a basis. How do I know that 1 is a basis? Well, I'm going to show you how, if you look at any complex vector, right? Let's take some vector out of this complex vector space C. I'm going to call that vector Z. I claim that is a linear combination of these basis vectors, by which, of course, I mean it is a scalar multiple, because it's just the one. This is a scalar multiple of that basis vector. And what is my scalar? Keep in mind, I'm allowed to pick any complex number now. So what scalar do I multiply by the vector, the basis vector 1, to get the arbitrary vector in C? Z. And, no surprise, I hope, but Z. Right? And that is a complex scalar. Oh, and again, I'm using yellow, and that doesn't show up well. Apologies. Let me change that to orange. Z. Right? And so, as promised, whatever vector you give me in this I mean, you're going to want to say two-dimensional, right? Whatever vector you give me in this plane, this seemingly two-dimensional thing, yeah, but it's all a scalar multiple of a single vector. So, in fact, the complex plane is one-dimensional. And that just, I mean, that's very counterintuitive and unsatisfying. And so you can see here that now, I mean, clearly complex scalars have messed us up. Yeah? Okay. All right. Whereas, just by comparison, and this is a nice exercise, I'll leave this as an exercise for y'all. If you want to think of the complex plane, colors. If you want to think of the complex plane as being a vector space over the reals, then here's a basis. You need the vectors 1 and I. If you're only allowed to use real scalars. Right? And so you can convince yourself without too much trouble that the numbers 1 and I are independent and that they span the complex plane over real scalars. Okay, all right, so clearly two-dimensional because I have two vectors in this basis. So big difference between complex scalars and real scalars. Okay. All right, here's a related situation. So I'm going to define Cn. This is highly analogous to Rn. It's exactly what you think it is. Rn is the list of all n tuples of real numbers. Cn is a collection of all n tuples of complex numbers. So exercises that I'd like you all to take on for yourselves. It has complex dimension n. It has real dimension 2n. This would be a nice practice problem. Okay, pause for questions. Anybody? Okay, so dimension definitely changes. And by the way, we are not going to actually spend any significant amount of time in this class talking about general complex vector spaces. It's just not really what this course is about. That'd be more of a Math 221 thing. We're going to talk almost exclusively about Cn. So we're going to do a bunch of stuff in Cn. But just as an FYI, I mean, complex vector spaces, it's just it's a generalization of Cn, just like real vector spaces are a generalization of Rn. It's the same kind of deal. Okay. So, what if I wanted to create an idea of an inner product space on Cn? Right? I mean, now, keep in mind, Cn is it's just Rn, pretty much, just where you allow complex coordinates. Right? It's the same idea as Rn. So, we made an inner product. We made a dot product on Rn by this formula right here. Right, the good old Math 212 dot product formula. Why can't we just use that same formula? It's very tempting. And the problem is this is a little bit weird, but on Cn, the dot product actually doesn't behave very much like the dot product. By which I mean this formula that we like to call the dot product on Cn does not satisfy the properties that we wrote down that we felt like were characterizing its behavior in Rn. It fundamentally changes, in other words. And specifically, it's that fourth property. Notice here is a very simple, easy to write down, innocent-looking little vector, and yet it's, using that old Math 212 formula, its self-dot product is 0. And you're not allowed to do that. That's fundamentally not what dot products are supposed to do. Yeah? Questions? Okay. So, if we're going to do this, if we're going to take Cn, if we're going to define something dot product like on Cn, we're going to have to adjust this formula. That formula doesn't work. Okay. So, here's the answer Here is the formula that most, I mean, this is going to sound silly to say, this is the formula that behaves most like the dot product, even though it doesn't look like the same formula. And it's an odd little formula, I'll grant you that. But here it is. It's called the Hermitian dot product on CN. We write it like this with the little triangular braces. You'll notice that those triangular braces look a lot like inner product notation. That's on purpose, right? So it's just notation. Notice also the little subscript of capital H. So that's our little doth of the cap to okay. Hey, this is not a regular real inner product. This is the Hermitian dot product. This is a dot product designed for CN, not for RN. Right. Okay. And here's the formula. It's still, you're going to be adding up a bunch of products related to the coordinates of these two vectors. The only little asterisk is that you have to conjugate all of the coordinates of the second vector. Seemingly odd little choice, but that turns out to make for a construction that behaves actually reasonably well. And it just is. This just happens to work. So what you'll notice is that the four properties that are satisfied here, these four properties, they're not exactly like the four properties of the dot product or the four properties of real inner products. But they're not that far off. It's just a couple of tweaks that result. If you switch the order of the vectors, no, it doesn't stay the same, but it just conjugates. So V Hermitian dot W is the conjugate of W Hermitian dot V. If you factor out a scalar on the right-hand side, you just have to conjugate that scalar before you factor it out. Right, a little minor little tweak. And other than that, everything's fine and dandy. All right, how we doing? Now, I made I guess you might say a mistake when I was first learning this. I thought, so if you're in RN, then you use the one formula. If you're in CN, you use this different formula. And for a long time, my first time learning this material, I thought, different formulas for different contexts. And then I made what I think is a very satisfying realization, which is that nope, it's always the same formula, actually. We just wrote it down wrong previously. So think about now this formula here. This formula. How would this formula look if V and W were both real vectors? If both of these were vectors in Rn? Well, if V has all real coordinates and W has all real coordinates, then, who cares if you're conjugating these coordinates of W? They're all real anyway. And so notice, in fact, it is exactly the real dot product on Rn. So we could have written this down in Math 212. Right? As the dot product formula for vectors in Rn, we could have written down exactly this. It just would have seemed super weird because why are we talking about conjugating real things? Right? It would have seemed totally arbitrary. But in fact, it's the same formula. This is just really a more sort of thorough, a more sort of fully accurate way of writing down the formula that we should have been using all along. So anyway, I think that's very satisfying. Let me pause again for questions. Okay. All right. Quick little cultural point. Like I was saying before, there are complex vector spaces in general. We're not going to really talk about complex vector spaces in this class. We're going to talk pretty exclusively about CN. And likewise, we're going to talk specifically about the Hermitian dot product on CN. That said, anything that behaves kind of like the Hermitian dot product could be viewed as a different Hermitian inner product on CN. And then likewise, you can also talk about Hermitian inner products on other complex vector spaces. Right? And so again, Math 221 will do more of that kind of thing. We're not going to do any of that in this course, but all of these ideas that we're going to talk through kind of sort of generalize in these other contexts. Okay, so like I said, that's just a quick cultural point. So moving along. By the way, let me give you a perspective on what we're doing here. This is just for kind of fun, but complex scalars. Right, we're changing something fundamental about the objects that we're studying here, allowing complex scalars, and we've gotten several new, sort of adapted, appropriately adapted to the circumstance, sort of adjusted ideas. So dimension, for example, right? This choice to allow complex scalars gives us a new, kind of vaguely familiar, but still very weirdly different notion of dimension. And likewise, complex scalars gives us a new, kind of vaguely familiar, but highly distinctly different notion of a dot product. So with these complex scalars, we've got a new notion of dimension, a new notion of dot product, and what we're going to find is that we keep getting new, different, weird, kind of similar to the old things, but still different and weird in their own new ways. And to me, it honestly feels a lot like Alice in Wonderland, where there's a lot of kind of familiar looking things, but they're all weirdly different. And anyway, we're going to find that continues to happen. Yeah.
So like when we first talk about it, it's kind of like coming from to understanding of angle, right? So
Yeah, well, in Math 212, yeah, right.
How is this on a CN related to intuitive notion of angle?
Yeah, we just don't motivate it that way, right? So what we have here is we're defining an operation. We're going to show that the operation, well, we've already seen that the operation has certain algebraic properties. But yeah, it's kind of hard to make sense out of the notion of angle in that situation. So in fact, I'll say even back in Math 212, when we defined the dot product, we wrote down a formula, and in that context, it happened to have certain features, right? So it's not really that different, right? It's just that it doesn't have that same. In other words, dot product is not really tied unavoidably to angle. That's just kind of a neat feature that it happened to have in that context. It's a great question. Yeah, thank you. Anybody else? Okay, so Alice in Wonderland. So be on the lookout for, we're going to continue to write down, this is kind of familiar, but boy, is it's a weird one, things as we go along. So here is the next, here's a segue into one of those things. So let's talk about regular dot products. I should say real dot products. I'm going to use inner product notation here, but that's just for sort of notational segue purposes. By this triangular braces, I'm talking about the good old Math 212 plain old regular dot product. So anyway, here's a property that relates dot products to transposes. And it's just a matter of writing it down. Remember, we wrote down this property a couple lectures back. You can think of a dot product as a transposed matrix product. Remember that? And having done that, and don't forget, transpose of a product is the product of the transpose, but don't forget to switch the order of the matrices. Right? You have to do that. And then you can move parentheses around. Instead of this, you could do this. And then notice what we have is a transpose matrix product of V and A transpose W. And so, as a nice little punchline, what we have, and that is, a weird fact, but the good old Math 212 dot product has a nice relationship with transposes. Namely, inside of a dot product, you can move a matrix from the left side to the right side if only you transpose it. So anyway, this is kind of a cute fact of what you might call matrix algebra, I guess. Right? Real matrix algebra. Okay, well, along the lines of our Alice in Wonderland situation, we now have an updated new dot product called the Hermitian dot product. Transposes play nice with regular dot products. Do transposes play nice with Hermitian dot products? And the answer is no, they don't. So next natural question to ask is, okay, well, since I've adapted the dot product to my Hermitian context, is there some easy way that I can adapt the notion of transpose to look, kind of vaguely like a transpose, but different in such a way that allows something like this to actually still be true? And yeah, it does. There's totally a way to do this. It's called the Hermitian Transpose. Here's the formula for it. We use this star to represent Hermitian Transpose. And the formula for the Hermitian Transpose is you just conjugate the transpose. And it turns out that works just fine. The Hermitian dot product relates to the Hermitian transpose in a way that is totally analogous to the way the good old regular dot product interfaced with the good old regular transpose. So, in our Hermitian world, in our Wonderland world here, this is what we're going to call the new notion of transpose, or more commonly we'll just say the Hermitian transpose. Okay, and so note, it's not this, right? This is transpose. The Hermitian transpose is not the same thing. It involves doing this, right? Flipping over the diagonal, but it involves a little bit more in order to make it fit in with our program of what's going on. How we doing? Everybody okay? Not clear where we're going with this, is it? Like, what's the point to all of this, right? Yeah. Yes. No. That's a conjugate. Yeah. So it's the conjugate of the transpose. Yep. Right. And so let me just remind you. It is this construction, this thing here, is kind of transpose-like in terms of how it plays with the dot product, right? But it's Hermitian. So let's see. It's kind of transpose-like in that sense, but it's Hermitian in the sense that it does so in relation to the Hermitian dot product. So thus the name Hermitian transpose. Okay. And by the way, another name for this, another thing people commonly call this construction is just conjugate transpose. And I think conjugate transpose makes loads of sense because you're conjugating literally the transpose literally of the matrix. So it's a very sort of like straight interpretation of the construction. Okay. All right. There's another couple of terms you should be familiar with. Hermitian conjugate. To me, I don't know. I've never really liked that term. I always feel like the term Hermitian conjugate is kind of saying conjugate. Right? There's no indication there that there's any transposing of any sort going on, so I don't like that one. But adjoint is another very common term for this, and it's also the standard term for a generalization of this idea that we are not going to talk about in Math 216. Okay, so adjoint, you'll totally hear that term as well. Okay, so new notion of scalars gave us a new notion of dimension. Gave us a new notion of a dot product, which has now given us a new notion of a transpose. Okay, well, so what does transpose relate to, and do we therefore get a new version of that? And it's an easy next step to take, which is, well, transpose is how you define symmetry. So in the same way that a matrix is symmetric if it's equal to its own transpose, we're going to say that a matrix is what I would like to call Hermitian symmetric if it's equal to its own Hermitian transpose. And I sure do wish that this was the common term, but unfortunately it's not. Unfortunately, the term is just Hermitian. Anyway, that's what people say. So heads up. When you see this word, though, when you see a matrix being described as Hermitian, what you should think in your mind is Hermitian symmetric, namely that it relates to Hermitian transposes in the sort of expected way. All right. So just to have it down on record, if it is its own Hermitian transpose, well, for a real matrix, being its own transpose means that it just moves over to the other side. You don't have to transpose it. It is its own transpose. Likewise, if a matrix is Hermitian symmetric, then you don't have to conjugate transpose it. It is its own conjugate transpose. All right. Okay, so we've built up a bunch of machinery, and there's some neat things that you can do with this. By the way, if you ever take a class in quantum mechanics, it turns out that, interpreted appropriately, one of the big important things you have to talk about in quantum mechanics is a specific vector space with complex scalars. And so these kinds of these kinds of constructions, these kinds of ideas play very prominently in studying quantum mechanics. So, for example, we're going to not do that in this course, but we are going to do some neat calculations about real symmetric matrices. Real symmetric matrices come up all the time, right? Real matrices, of course. Here's an easy example. Do y'all remember in Math 212? Y'all remember doing optimization, and you encountered this thing called the Hessian matrix. Y'all remember the Hessian matrix? Yeah. Okay, so that's this thing that you look at when you're applying the second derivative test, and there's other things that you can do with it. But it turns out that the Hessian matrix, by the way, is the matrix of coefficients in the second order Taylor polynomial for multivariable functions. That's kind of neat, right? I mean, Taylor polynomial, we know is a big deal. Well, there's a multivariable Taylor polynomial, and the Hessian matrix divided by 2 are the coefficients in that thing. And if you want to see those details, come to office hours. I'll show you how that works. It's not that big. Okay. So the Hessian matrix is symmetric. The Hessian matrix is a real symmetric matrix. So, therefore, a nice important example of what we're about to study. And it turns out real symmetric matrices have some amazing properties, largely because of the fact that they are Hermitian. It's easy to show that they're Hermitian because, keep in mind, to be Hermitian, you need the matrix to be its own conjugate transpose. Well, if it's real, then it is its own conjugate. And if it is symmetric, then it is its own transpose. Right? So if you have a real symmetric matrix, its conjugate transpose is just itself. Thus the matrix is Hermitian. Okay. All right. So what follows is a couple of remarkably magical little proofs that seemingly come out of nowhere, but there's some powerful results. Here's the first one. If you have one of these matrices, real symmetric matrices, in other words, any Hessian matrix, right? You have a real symmetric matrices, then the eigenvalues are all real. You'll never find any complex eigenvalues. How about that? And furthermore, and I'm going to say the eigenvectors are real. What I mean by that, now I've written this down more accurately. The eigenspaces all have bases consisting exclusively of real vectors. But if you have a real eigenvector, all real coordinates, you can multiply by a complex scalar, of course, right? But what's not obvious is that you can find a basis of the eigenspace that consists exclusively of real vectors, purely real vectors. So again, lingo being kind of inconvenient sometimes, the sloppy way that I'm going to say this is I'm just going to say all real eigenvectors. In other words, when you go through and you find the eigenvectors, what you will find, which in fact is just a basis for your eigenspace, but what you will find are all real vectors. Alrighty, so this is what I like to call a mathematical bank shot. It's weird how this works. We're going to prove a result by starting off by calculating something that we seem to have no interest at all in. Right? You all have seen examples of proofs like this before. So here we're going to consider, for no apparent reason, this little construction right here. Right? So suppose you have some eigenvalue. Take some eigenvalue, and suppose we have a corresponding eigenvector. Don't forget, eigenvectors are non-zero. Right? And let's just see what happens when we think about the Hermitian dot product of AV and V. Not at all clear why we would care, but here we go. So this thing, remember, the matrix is Hermitian. This matrix A, being real and symmetric, it's Hermitian, so I can toss it over to the other side for free. We showed that. Now, don't forget as well, lambda is an eigenvalue and V is one of its V is one of its eigenvectors. So AV is lambda V. I mean, that's just, just write it down. Okay. And, well, constant factors out. Yawn. Constant factors, wait a second, it kind of factors out, but you do have to put in the conjugate there when you factor out scalars from the right-hand side. You have to conjugate the scalar. Remember, we wrote that down. That was one of our observations about our new Hermitian dot product. So you get that. We went to a bunch of trouble to try to make sure that that this is non-zero. Right? The whole reason we had to write down our new formula for Hermitian dot product in the first place was because the old, the sort of the naive Math 212 formula for dot products didn't have the feature that non-zero vectors must have a self dot product that was zero. It just didn't work. We saw an easy counterexample. It just doesn't work, right? We made our new Hermitian dot products specifically in order to try to preserve as much as possible, but specifically with the idea in mind if we wanted to have self-Hermitian dot products never be zero. So, this is not zero, and you can therefore cancel that common factor, and therefore lambda is its own conjugate, and therefore it's real. And it's just amazing how this just falls into our lap like that, right? We started off thinking about something that we did not immediately see why we could, why do we care about this construction at all? But there it is. Our result that we wanted, the eigenvalue is real. So like I say, it's a little bit of a magic trick. A little bit of an oddity, but we developed a construction. We showed that it had certain key properties. We're doing perfectly legal algebra here, following, strictly speaking, the properties that we wrote down, strictly speaking, based on the definition that we wrote down. But it's all legal. And amazingly, non-intuitive though it is, this all this formality nonsense gives us this very powerful conclusion. Okay. All right. Now, second thing that I claimed in this theorem is that the eigenvectors are all real. Again, speaking sloppily. How do I know the eigenvectors are all real? The second part is actually much easier to prove. How do you find the eigenvectors? Well, you take your eigenvalue, which we know is real. You do a row reduction of lambda I minus a. Well, wait a second. If lambda is real, we know I is real. By assumption, a is real. we're therefore row reducing an entirely real matrix. Row reductions don't involve any square roots at any point, right? So if you start with a real matrix, when you row reduce, of course the results are all going to be real as well. And therefore you get your real eigenvectors too. Okay. All right, so we're going to have to call it a day there. We'll pick up here on Wednesday. Y'all have a nice day. See you later.